Hello. What we're going to do today is get to the real thing, which are theorems and proofs. Real proofs. We're not easing our way into it anymore. We're actually falling off our desk here. That wasn't very good. We're going to prove real theorems. Doing things much the same as we did in the last two videos, really. Except this will be a little bit more formal. Only a little. And this won't really be very hard. Remember, a theorem is a statement that can be proven. It's not like a postulate or axiom or definition, which we accept without proof. These theorems, we use our axioms, postulates, definitions, and anything else we can find to prove the truth of the statement. For instance, let's consider congruence. We have some properties of equality which we didn't prove, we accepted them as pretty much postulates. What about congruence? Well, we don't have to accept anything with respect to congruence, at least not much. We can prove it. So let's take a look at, there it is, some possible properties of congruence. Reflexive, symmetric, and transitive. Do these properties hold? Well, this is just a theorem right now. We'd like it to be true. It seems like it should be true. But how do we know that it's true? Well, it's pretty easy, really. AB is, of course, without the line. Oh, darn. If we write AB this way, that means the length or measure of AB. We'll call it the length of the line segment AB. With the line over it, that is the segment itself. Now we have a reflexive property, which already tells us that AB, this is the length of AB, is equal to AB. However, the definition of congruence would imply that the segments AB, well, I say segments plural when it's really only one segment. We're treating it like it's two different ones. Is AB, the segment AB, is congruent to itself. That probably didn't rock your world any more than this did. And all these proofs were just the same way. All you have to do is write down what you know about the length of the segments. For instance, if we drop the segment symbol so that this is the length of AB equals the length of CD, and the length of CD equals the length of AB, then we know from our transitive property of equality that the length of AB what the heck? Hold on a second here. It doesn't seem right to me. Yeah, this follows from the properties of equality. I was talking about the transitive property and pointing at the symmetric property. So let me get my act together here and do this right. If the line segment AB is congruent to the line segment CD, then we can reverse it and the congruence still holds. Why is that true? We just use our properties of equality. If AB segment is congruent to segment CD, that means that length AB, that's just from the definition, equals the length of CD. And we know from our property of equality, that is the symmetric property of equality, that CD equals AB. from the definition of congruence, that implies that CD, the segment, is congruent to AB, which means that the symmetric property holds. And you would do exactly the same thing here. There are also three theorems, reflexive, symmetric, and transitive, for angle congruence. You could just insert the word angle up here. And you would prove them exactly the same way. Instead of the length of the segment, you would use the measure. For instance, if two angles are congruent, by definition, their measures are equal. So you write the equality, use the properties of equality to arrive at the particular rearrangement, whichever one you want here, and then use the definition of congruence to go back to showing that that rearrangement also holds for the congruent objects, just as it held for the equalities. Real easy. Now that you're hopefully convinced of the truth of these theorems, let's take a look at what a two-column proof really is. That's one of the things that we're going to have to study here. It's very important because you'll see it on the standardized state exams. And it'll be along the lines of things that we did in the previous video, where they will show you parts of the proof filled in and parts left blank. And it'll be up to you to fill in the blanks. For instance, let's take a shot at redoing this in the two-column proof form and see what happens. And now that we've done it this way, it's just kind of and I just said the word kind of again. I'm sorry. We did it this way and just laid it out and talked over a lot of this stuff to demonstrate that this could be proven very easily. And you would use the same technique to prove all of these. And the same is true for these theorems on angles. However, this is definitely not a two-column proof. It barely qualifies even as a proof, the way I laid it out, because I was talking as I was writing, and without the narration that goes with this, you may or may not accept this as a proof. Down here, this is more like the legitimate, every step is laid out kind of proof, where without any narration at all, you should follow this very easily. We're given the segment AB right here. Sometimes that's the hardest part to write, is the given, because you have to reword what's up here. You could just write AB with nothing else, I guess, with a line over it to say that AB is a segment. That would probably be the shorthand version of given. I would write it this way. We're given that AB is a segment. Now, we know that AB as a length, the length of AB equals the length of AB. That is the reflexive property of equality. We use this property of equality a lot. Reflexive, symmetric, transitive property of equality. Addition, property of equality. Multiplication, property of equality. Turns out to be a lot easier to just write POE, which I think it is. As it gets used a lot, I abbreviate property of equality with PO. And this is true because of the reflexive property of equality. Not congruence. We don't have a property for that, for congruence yet. We're about to, because our next line is going to give us that. This is the definition of congruence. If two segments have equal length, then they are congruent. So we can rewrite this as a congruent relationship. And now we have a reflexive property for congruence. The big difference is the reflexive property of equality is something we just accept. The reflexive property of congruence is something we can prove once we've accepted this. See, they're not quite the same. And the important part here is the format. It's called a two-column proof because we've got a column of statements here and then a column of justifications right next to it. It's two-column proof. The most important thing is following the logic. For instance, in the books that you read, algebra, if you go on to study AP calculus or more mathematics in college, when they prove things or demonstrate the proof, it will almost always be in a paragraph proof. It flows better. For instance, verbally, a paragraph proof would be something like, given that AB is a segment, then the length of AB equals the length of AB by the reflexive property of equality. And if AB equals AB, then from the definition of congruence, segment AB is congruent to itself, or segment AB. If you wrote all that out, that would be a paragraph proof. And if you want to do some reading, you could even find out about other forms of proof. It's all kind of unnecessary, really. As I said before, what matters is the flow of the logic. You have to get the steps in the proper order and then justify them correctly. If you do that, then you have a valid proof. The emphasis on two-column proofs is primarily because that's what you will see the most of. In fact, almost exclusively, I think, in the standardized state exams that you will eventually be taking. But there's nothing magical about the two-column proof. That's just the one they decided on. It's a nice, simple way to lay it out. Wow. You could write it on, well, if you're into graffiti, you could write it on the side of a wall and call it a wall proof. Write it on the bottom of your shoe and call it a shoe proof. Okay, so what matters is the flow of the logic. Get that right, and it doesn't matter. For instance, that's a valid proof. I call it a rubber chicken proof. It's not what you see in most math books, but it's perfectly legitimate. We've got step 1, 2, 3. It's very much like a paragraph proof, except in rubber chicken dialogue. It's totally valid. There's nothing wrong with doing that. So keep in mind, it's the flow of the logic that you're most interested in. Get the statements in the right order and get the justifications right. Exactly how you lay that out really isn't that important, except on the standardized exams, you need to practice the two-column version. When you start working on your PhD in mathematics, you may want to do more work with rubber chicken proofs, but for now, stick with the two-column proofs. And you can have fun with the rubber chicken proofs if you want to on the side. And when I wrote this two-column proof, I forgot to put the headings up here on top. I think you figured it out. These are all the statements, and these are the justifications. Now, I think what we should do is work some more problems out of the book, see how this stuff all works out. And here we have, just as I mentioned, a two-column proof with something left out, and we get to fill in the blank. Note the absence of rubber chickens anywhere. That's how you know this is a two-column proof. What are we given? We're given this stuff here. So we write that in our first line. That's pretty much always going to be line number 1 in your two-column proof, whatever you're given. And line number F, that would be final line. However many lines there are, the last one should be this. So you get your first line and your last line written for you. All you have to do is fill in the stuff in between. Well, let's see how this one works out. Okay, 59 degrees is the measure of angle 2. Now, later on, in other math classes, and even in this one, there are many properties of equality which are so common you don't even bother to write them. This section we're studying properties of equality, so we're writing them out. In other more advanced classes, and maybe even later on in this class, we might not go to all the trouble of writing this totally obvious statement here. But these totally obvious statements is what we're studying right now, so we have to write them out. Symmetric property of equality. M1, measure of angle 1 is equal to the measure of angle 2. Well, how do we know that? I would say I would write substitution in here. But they didn't list substitution as one of the options, did they? Why would that be? So I'm going to digress a little bit because it gives us a good opportunity to take a look at something here. This is the substitution property of equality. This is the transitive property of equality. And this is the one for angles. I listed it because we happen to be working with angles. Now, as we said before, this one just says that, written out this way, measure of angle the measure of angle A equals the measure of angle B. The measure of angle B equals the measure of angle C. Then we can just jump right over the measure of angle B and go straight to the measure of angle A equals the measure of angle C. Okay, but suppose up here I have the measure of angle A and the measure of angle B are equal. And over here I have an equality which uses the measure of angle B. And from the substitution problem, I can substitute right in here measure of angle A equals measure of angle C. And I have the transitive property. So there's a definite relation between these two. You could even say that, strictly speaking, a mathematician would call these redundant. One of these should be an axiom. One should be a theorem. But this is high school geometry. We don't have to be perfect. We can just be reasonable. We'll get didactic when we get to college. And you can really impress people with all the stuff you know how to do. For now, accept the fact that there's a little bit of overlap here. I jump to substitution immediately because it's so common and works so often all over the place. And if you were to do that, you could then, given this, just substitute measure of angle 1 in for 59 and arrive at this. However, there is something else going on here. They rewrote it this way for a reason. Why? So it would exactly match the form of our transitive property of equality. Just substitute 59 for the measure of angle B, substitute 1 for A, and 2 for C, and we have exactly the form of the transitive property. When we've reversed this into this, now these two lines form exactly the transitive property of equality. Written this way is totally obvious. We just jump right past the two 59s and write measure of angle 1 equals measure of angle 2. And that is the transitive property. If they had written, if substitution had been one of the options, I guess me and the authors would be arguing for a while. Luckily, that wasn't one of the choices. So, transitive is definitely the right one. But I don't see anything wrong with recognizing that these two are extremely related, and you could actually derive one from the other. And here's one that you hardly even have to think about. This would not be the reflexive property. The reflexive property would say that segment CD is congruent to segment CD. And of course, where it says property of equality and property of equality, we can forget both of those because this is a congruence relation right here. So, symmetric property of congruence and property of congruence, these are at least possibilities. Since we have a congruent symbol up here, just forget these because they just say property of equality. Not quite the same, are they? And I would say this is definitely the symmetric property of congruence. This really has nothing to do with transitivity. But symmetry, well, yeah, I mean, just look up the English definition of the word symmetry or symmetric, and you can see why this is called the symmetric property of congruence, because it is symmetric. Pretty easy. Okay, here's another easy one. You could probably do this in about 5 seconds. We have, well, this is like just the statement of transitivity. I mean, this is like the first 2 lines of the statement of the property of transitivity. The third line, of course, would be this one. But when they write this, they say by the reflexive property of congruence. Oops. No. That's by the transitive property of congruence. That's all there was to this. Pretty easy. Just what he wrote is true. This statement is not wrong, but that's not the reason that it's right. It's not reflexivity that allows it to be right. It's transitivity which allows it to be correct. Here's another one. Again, repetition is how we learn. And these 2-column proofs, well, it might seem like a drag to you, but it's not that bad. They started doing it this way, I believe, because it's much easier to grade this kind of a thing with the standardized tests. 100 years ago, students had to actually just pull all this out of their own head. They didn't fill in the blanks. They said, given this, prove this, and that's all you had was a blank piece of paper. You had to figure out all the steps in between and each justification. Now you get a little bit of a break. So before you start hating this too much, remember that it could be a lot worse. This, like I said, the first line is always given. Maybe I should double check and make sure this really was given. RT equals 5, yes. RS equals 5, yes. And the segment RT equals this, pardon me, segment RT is congruent to the segment TS. Yeah, that was all given. RS equals RT. Transitive. Okay. Notice they didn't go to all the trouble to rewrite it. To have to rewrite this as 5 equals RS and then have it in exactly the previous form and then apply the transitive property. They just accepted that you can mentally make that switch and apply the transitive property. And I'm sure they're right. You can do that. Definition of congruent segments. Yes, now here it says that they're congruent over here. And what is the definition of congruence? Well, for segments, it means that their lengths are equal. So, RS equals TS. Well, here they have this in exactly the form of the transitive property of equality. So, you just cut off the middleman, set these 2 equal. RS equals TS. These are the lengths of the segments. And this says, next line, which of course is what is to be proven. That should always be your last line. segment RS is congruent to segment TS. Why? Definition of congruence. In fact, that's the same as number 3. Notice we used the transitive property here and used it again here. That's okay. Don't start thinking that you only get to use these properties once in any given proof, and then you got to find another way to do it. For instance, a transitive property, but then you got to use substitution here because you don't want to use transitive twice. No. You could have 5 steps in between the first step and the last step, and every single one of them could be justified by exactly the same postulate, axiom, or even theorem. See these justifications over here, after we start proving theorems, we can use theorems in here instead of axioms. And we can combine them. We can use axioms, theorems, and definitions all in this second column here to arrive at our final result, which is what is to be proven. So don't worry when you end up citing the same property or axiom more than once. That's no problem. That's going to happen many times. Now we're going to solve an algebraic equation. And we're not going to do too much in our head the way I frequently do these algebraic equations. We're going to do it step by step in a 2-column format, because a solution to an algebraic problem really is a proof, even though you don't usually think of it that way. You have a sequence of statements, which are rearrangements of the original equation, and then a justification for each rearrangement. And that's exactly what we're going to do here. So let's start out with what we know. I wrote it in 2 lines because I ran out of room. That's allowed. You could write given, given, or just one great big given right here. That's why I drew a line under this to indicate it. These are both given. I just didn't have room to put them all on one line. That's actually legal, I think. If it isn't, please don't tell anybody. Now, well, what else can we do here? First thing to do is just see what statements lead to. For instance, we have a given statement here. What does this lead to? Well, we have QR equals PQ, pardon me, QR is congruent to PQ. RS is congruent to PQ. So how about we use our property of transitivity for congruence to write that QR equals, or QR is congruent to RS. Okay, so far, fairly easy. And that is the transitive property of congruence, POC. But that, it's tempting to just jump right in and write 2x plus 5 equals 10 minus 3x. Strictly speaking, we're skipping a step, I think. Although, if your instructor did it that way, don't tell him he's wrong, because it really is probably okay to do it that way. It's just kind of a jump. But let's do it this way to make sure we get every possible step listed. And that is that the length of QR, which is written without the line over the top, is equal to the length of RS. That comes from definition of congruence. I'm going to write C. It's the same C that's up there, property of congruence, definition of congruence. However, our diagram says that the length of QR equals this. But it's not actually stated, is it? So, maybe we should have written it up here in the given. That would be the right way to do it. So, let me modify this and do it the right way. I could have written given 4 times. I just wrote it one great big capital given, so I'm screaming the word given here. It's all of these. Now, at this point, down here, I could have written these two down here and written given next to it. Given doesn't all have to be up here on the top. You could write it in when it becomes necessary, when you're actually going to use it, if you think it improves the flow of the proof. I put it up there, redid it with it all up at the top because I've been using that format all along. At this stage, there's no point in adding to the confusion. So this is given because it's written right here, even though they didn't state it up here. I would list it as given. And the fact that they didn't list it up here, well, that's one reason I didn't put it in the first line. In a regular proof, you might actually list these two given statements up here farther down here when you actually use them. But that's okay. We're going to do it this way. Up here we have QR equals 2x plus 5, RS equals 10 minus 3x. So let's substitute and get that 2x plus 5 equals 10 minus 3x. And that's the substitution property of equality, because we're dealing with actual numbers here, not congruent objects. Okay, so what do we do next? Question is, can we do two things and just cite the law of substitution? Pardon me, the law of addition? Most of the time we could, but since we're just learning this, we're going to go ahead and write it all out one step at a time. And first step would be, I would say, add 3x to each side and get 5x plus 5 equals 10. And that would be addition. Property of equality. What do we do next? Subtract 5 from each side. Or add minus 5. Now I'm going to stick with my philosophy that subtraction, wow. Well, I would stick with it if I could speak, but I seem to have lost that ability lately. The addition property of equality and the subtraction property of equality are really the same thing. What I'm doing here is adding minus 5. So I call it the addition property of equality. However, if your teacher says this is a subtraction property of equality, he's right, it is. I'm just kind of lazy. I tend to stick with what's simple. I think it's a lot easier to remember two properties of equality rather than 4, and then remember the additive fact that addition and subtraction are the same thing, multiplication and division are the same thing. I think you already know that from Algebra 1. Hope I'm not throwing a bunch of stuff at you that's super confusing or anything. Anyway, the division property or the multiplication property, and I would say multiply by 1/5, 1 over 5, and get that x equals 1, and that is the multiplication property of equality. So what we have here is, on the one hand, it's a proof. I have just proved that x equals 1. On the other hand, it is in fact a solution. And I've done things exactly like this in previous videos, but when I did it, I skipped all this stuff, didn't I? I just immediately wrote, well, we're given that this is equal to this, so let's just set up our algebraic equation. This equals this. Boom, boom, boom. And we're here. And chances are, when I did it, being the lazy guy that I am, I combined these two steps all together and just immediately wrote that we add 3/6 here and subtract 5 here and get this, and then divide through by 5 and get this. So we're doing this the long way in order to demonstrate how proofs are done. Here's a nice one. You don't have to come up with everything just off the top of your head. All you have to do is look through the options here and see which one fits the line. I think it's easier that way. It's easier than just coming up with the whole thing by yourself. So all I'm going to do is I'm going to write the number of the statement over here on the right, or write it all out or rewrite it, or that kind of stuff. So our first statement should always be what's given. Let's make sure that that is. Well, I would say that this sentence is just a perfect copy of this one. So that would be D. And to make life simpler, once we've used one, let's cross it out so we don't keep wondering if we need to use that again. The reason I'm doing it that way is because they listed they listed 7 of them here and 7 here. They don't say that we're going to use each one exactly once, but I'm pretty sure that's how it's going to work out. I'm not sure you could make that assumption on a standardized state test. Now, we have that this ray, QS, is an angle bisector of PQR. So we don't know what kind of an angle PQR is. It could be obtuse, it could be right, and it could be acute. So let's just draw an angle and see if I can draw something that looks kind of like a bisector. It's not very good, but let's just pretend that that is the bisector. There's Q, there's S, over here somewhere, I guess. And here's P and R. Okay, so PQS, that's this one here, and SQR, that'll be this one here. They must be equal because they tell us that this is a bisector. So that would be the definition of bisector. Well, here it is here, definition of angle bisector. So let's cross it out and write A in here. These two are equal by the definition of angle bisector. And of course I've already made a mistake because I said equal here. Really bad habit. They're not equal, they're congruent. Definition of angle bisector is that it breaks it up into 2 congruent angles, or these congruent angles are congruent because they have equal measure. That's the definition of congruent angles. And is that up here somewhere? There it is, F. Okay, so we just used F. Definition of congruent angles. What about this one? PQS, that's this, plus SQR, that's this, equals the big one here. And that's our addition property for angles, isn't it? There it is there. Angle addition postulate. Let's see. Cross that out. By the way, that's supposed to be an F. Write it out here where I got one. There we go. This is true because of the angle addition postulate. Okay. Why would this be true? Aha. Well, what did we do? PQ, the measure of PQS, is equal to the measure of SQR. So we can substitute, can't we? We can just replace PQS with SQR, or replace SQR with PQS, which is what we did here. That's the substitution property of what? Equality, not congruence, because these are actual measures, not objects. So we can cross that one off. We used it right here. Substitution property. Now this one, okay. It's not obvious, But this is the distributive property from here to here. Why is that? Well, rewrite, yeah. I'm trying to figure out a lazy way to do it. I don't do so much writing, but I'm just going to have to do it the hard way and write the PQS 1 times measure of angle PQS plus 1 times the measure of angle PQS. Now, distributive property. Remember this whole thing right here, measure of angle PQS. This is all just a number, and this is all just a number. In fact, they are the same number, and these are the same number. But what I'm going to do is I'm going to pull this out. This is going to be like almost like our coefficient in a sense. If I pull this out, I get measure of angle PQS times 1 plus 1. What I do is I factored this out. I used the distributive property in reverse. Factored out measure of angle PQS and wound up with 1 plus 1, which of course is 2 times the measure of angle PQS. That's why the distributive property is what justifies this step here, even though it's not immediately obvious from the way it's written here. Now that we have this, how do we get from here to here? Well, I should have scratched out the B there. The only thing left, assuming we're going to use each one, is the division property of equality. And that, in fact, is correct. If I was writing this, I would say the multiplication property of equality and say multiply by 1/2. But this is legitimate. It's in lots of books. And we're all done. Maybe I should have written in the last one here, E. But this is what you're going to do when you see this on a test. You just go right through it. The first one will almost always be given, but double check and see that it matches up the line here. And then just go through and try to figure out how you would get to this next step and then look for that reason over here. If you can't see any way to get to that next step, then you can start looking at reasons and seeing if any of them jump out at you. But I would try to form my own answer first before I looked at these. If you think you'll have better luck recognizing it rather than coming up with it on your own, go for it. That's the cool thing about these kinds of problems. You can make use of what's written here, see if it'll jog your memory or not. Sometimes all the extra words just confuse me. I'm better off just coming up with the answer on my own and matching it up over here. You might do better a different way. Do whatever works best for you. That is the one rule in everything. I don't care if you're playing golf, tennis, or doing math. Just do what works best for you. And that's about it for, what was the name of this one? Proving segment and angle theorems. And we're going to do more of that. Lots of theorems in geometry. And come up with probably more interesting results than what we have here. Just totally off